Okay, so today our job is to go through chapter one. Um, Before I get there, though, I want to just talk about kind of some general things with the summer term. So first of all, obviously, I'm Julie Emerson. You probably guessed that. Um, so the way that this is going to work is every Tuesday and Thursday, I'm going to do my live online lecture. I'm going to use my chapter notes. So those notes are actually posted for you in my courses. Let me show you what the chapter one notes look like. So this is exactly the same thing I use in a face-to-face lecture. So you can go with me. Sometimes I'll highlight some things, I'll write some notes. The other thing you'll notice is there's examples for us to work out together. So everything is basically here. You're still actively learning though, because you're still writing information down, highlighting, etc. So a lot of my students like to print those out and have those for the lecture class. Since I'm going to spend the next 5 or 10 minutes going over the syllabus, if you want to go print out the chapter one notes because you hadn't done it yet, feel free. You probably won't miss anything that you can't get by reading the syllabus. All right, so what I jotted down here, just some kind of basics. The notes I mentioned, I hope that I'm going to make this look pretty easy. That's my job, is to hopefully teach chemistry in a way that makes it accessible. Fun would be great, but that's that's up to you. Then you have to practice. That's the part I can't make you do. I mean, I can try. And the way that I'm going to try to make you practice is there are quizzes in each of the chapter folders. There are practice quizzes, which are unlimited time, unlimited attempts, and they're low stakes. They're only a point apiece, and you can take them as many times as you want. Then in each chapter, except for the chapter right before the test, which I'll explain when we get there, in most of the chapters, all the ones that are highlighted below, there will be a credit quiz. And on the credit quiz, these are timed. So I'm starting to ask you to, be responsible for the information. So they're timed, you only get one attempt, and they carry more weight. They're 25 points. So those are two ways that I need you to practice. The practice quizzes, they're not really worth a lot of points, but they are worth points. So you still want to do them. And they will help prepare you for the credit quiz, which is worth more points and always do a week after we finish the lecture. Now, the dynamic study guides, these are on the Pearson site. So I'll show you where that is in just a second. This comes with the textbook. Now, textbooks are always a big issue, I think. For me personally, they probably are for you as well. They're super expensive. And then they will change the edition ever so slightly by like putting in a couple extra homework problems at the end. And now all of a sudden you have to get the new edition and it's $300, where there really isn't anything beneficial to that new edition. Anyway, it is what it is. So the way that you're going to have your book here, unless you want a hard copy, but if you're okay with the ebook, is this is part of the first day program through the Barnes and to the bookstore. And so the textbook is actually already embedded in the course, which is really nice. And it's an ebook, so it's not too expensive, but to at least give you some benefit to having this, except for, of course, being able to read the chapter and do homework problems, is I will assign these dynamic study guides. And these are meant that if you go through them, follow the directions, you should get 5 out of 5. And these are going to be your bonus points. And this is the extra credit that will be on the test scores. But I'll explain why I keep them separate in just a minute. So those are two things you definitely do not want to miss out on, right? So the quizzes, they are graded. So you definitely want to do those. Those are in each of the chapter folders. The dynamic study guides, which are in the Pearson website, those are extra credit. It's a lot of points. Definitely do not miss out on those extra points. Then there's two additional ways that you can practice. In each of the chapters, I go through and I pick out what I think are very good homework problems. They do a sample of a little bit of everything that we talked about. It's just an additional source of practice. And the answer key in the back of the book, which is called back matter, which is weird, but on the Pearson site, that's what it's called. Anyway, the answer key, a lot of times it'll just show the answer. It doesn't tell you how you made a mistake if you did. Like if you don't have the same answer, you may not understand what you did wrong. So I have gone through all those homework problems and done them myself on paper, and I've scanned and posted that. So the answer key is also, my answer key is posted in the chapter folder. So you can see how I did the problem. I might write some notes about sig figs or whatever it is. Anyway, and then you can definitely check your work that way. There's also one additional source of practice, and that is in a lot of the chapters, I will have a supplemental worksheet. And again, that worksheet, you can print it out, do the problems, and then there will be an answer key posted as well, so you can check how you did. So lots of ways to practice. I think a lot of my students only do the two that I purple starred, but the students that do really well in the class and are super successful, they do at least 3 of the 4 that I have listed there. All right, so here's how it's going to work. We're going to do chapters 1, 2, 3, 4, and then we're going to have test 1. Chapter 1 will have a credit quiz. Chapter 2, Chapter 3. Chapter 4 will not have a credit quiz because it's right before the test. And so rather than having you worry about the credit quiz, I just want you to start worrying about the test. Now, there are practice quizzes to help you practice the material, though, but there won't be a credit quiz. After test 1, we're going to do the same thing with chapters 5, 6, 7, and 8. Then we'll take test 2. Then we do chapters 9, 10, 11, and 12 and take test 3. Then your chapter credit quiz is always going to be due 1 week after we finish it in lecture. So for example, we're doing chapter 1 today. And so that means by next Monday at midnight, which I know is Memorial Day, your chapter 1 credit quiz will be due by midnight. All right. And then Tuesday, I'll get it graded. Then the cumulative final at the very end of the semester, we will have a Zoom session devoted to preparing you for that. Your final exam can count twice if it replaces or is better than your lowest test score. So you're either going to have exam 1, exam 2, exam 3, and the final as your 4 test grades, or it's going to be 2 of your best test grades and the final exam counting twice. It will replace your lowest test grade as long as it's a higher score. And with my class last semester, probably at least half of the students, it ended up replacing their lowest test grade. So we are going to have a total of 9 of those credit quizzes. I'm going to drop your lowest one. So if you miss one, it will not hurt you. They're 25 points apiece. So that's going to total 200 possible points for just the credit quizzes. Then you have 4 exams. They will be monitored with Respondus. The quizzes will not, but the exams will be monitored with Respondus. And those are 200 points apiece. So that's a total of 800 points. The 30 practice quizzes, as I mentioned, those are just 1 point apiece. So that's 30 points. And then those dynamic study guides that are on the Pearson website, that's a bonus of just about 6% added to your grades. So definitely do not miss out on those points. All right. And then this is a little bit that everybody's always interested. If you have an A on all of your exams and not an A on every credit quiz, but an A overall. So out of 200 points, you have at least 180, 90% on your quiz total, then you will be able to exempt the final. And that usually happens for at least a handful of students, which is always nice. All right, so that's kind of the first basics of policies. Next thing I want to do is share my screen really quick. And we're going to go in and look around at my courses and just kind of show you. When you go into course content, you all found the Zoom links, which is great. I did post them in 2 spots. They're on the course homepage, and then I just made a folder that they're here for you as well. Now, the Pearson book, all right, if you've looked at this, great. If not, you're going to go to the first day course materials, all right, and then you scroll down, and it says this is the link to your book. So you're going to open that up. And then it's kind of clicky. So from here, you're not done yet. Now you got to launch the courseware. And why isn't it working for me? There we go. All right. And then this, I think, is where your graded assignments will come in. Mine's going to look a little bit different just because I'm an instructor. But then I'm going to open my lab and mastering. And then what we're going to get is kind of a table of contents. So if we go over here to the left, you'll see the Pearson e-text. And if you're looking for those homework problems or just to read the textbook, so again, another click, open my book. I feel like this one's just really very clicky. All right. Why did that pop up? Let's see. Okay, well, I'll have to figure that out because it was working for me yesterday. So I love it when things go like that. Okay, normally what happens is when you open your Pearson e-text, you'll get a table of contents. I'm just going to try it one more time because that's really strange. Yeah, okay. I don't know. Anyway, anyway, you go to the table of contents, and if you want to read chapter 1, for example, it's right here. You can go through and read it over if you like. If you just want to skip to where the homework problems are, scroll to the bottom of chapter 1 and you'll see exercises, not the quizzes or the chapter in review. Just go straight forward to the exercises. All right, and then these are where I've assigned the homework problems from for you to practice. Not all of them, definitely not, just some that I've asked you to maybe think about. If you want to check the book answer key, not mine, but the book, you can go to the very back of the book, just like you would in a normal, hard copy textbook. And at the very bottom of the table of contents, you'll see this thing here that says the back matter. All right. And then in here, this is where you're going to get answers to selected exercises. And that's where you could find the solutions manual, for the textbook. Okay, so that's if you want to access any of the chapters and the homework problems. Now, the homework problems that I've assigned, if I go back into my courses and I go back into course content, and then I'm going to go into the chapter 1 folder. All right, so for chapter 1, what we have on our task for today, right, you'll see I usually give you a little description. So we're going to go through the chapter 1 notes. The dynamic study guide, you'll find those on that Pearson website, like we just talked about. I need to admit some students here really quick. All right, and then with those dynamic study guides in the Pearson site, this is kind of a good way to learn the chapter. So we've done the notes, you learn the chapter as you go with the dynamic study guide. These are your bonus points, so definitely do not forget to do those. And then your practice, right? So you have a couple of things to practice, like we talked about. First thing is when you want those chapter 1 notes, if you do, the files that I'm going to be using for each of our Zoom sessions, this is the file that you can print out. These are my notes. This is what I'll be taking my notes on when we go through the lectures. The homework problems that you would get in the TRO textbook, these are the ones here at the end of the chapter, the exercises that I just showed you. These are the ones that I would assign. I try to pick a little bit of everything, that we cover in the chapter. Now, if you want to check my answer key, this is the homework answer key with all of my writing on it, my notes, like anything that I've done for the problem, there's the answer key. Now, for the lecture, I'm going to obviously be recording our Zoom sessions, but sometimes you just want to revisit one topic and you don't really want to have to scroll through an hour video just to review significant figures. So I tried to take those videos and break them up a little bit. This was when I was very first starting my document camera, so the sound quality isn't as good, but it'll work, right? If you just want to look at sig figs, you can watch video part 2, right? You don't have to watch a full hour or 2 hours of videos to find it. It's just right there. All right. I will say that if I make a special video on a specific homework problem, I've got 2 for chapter 1. I definitely would spend my time watching those videos. Hint, hint. Okay. And then I'm going to post the Zoom sessions for you here as well when we're finished with today. As I mentioned, extra worksheets in the chapter for more practice. Then here's the practice quizzes. All right. And so again, these are graded, but you can take them as many times as you want, and they're open for the whole semester. And the reason for that is this is something you can use to help you review for the final exam. So that's why they're going to stay open. Highest score is always recorded. So if you take it, you get a 1 out of 1, and then you're reviewing for the final and it's been a while, so you get a 0.5 out of 1. Don't worry, the 1 is going to stay in the grade book. All right, so there's your practice quizzes. And then at the very end, this is the credit quiz. This is 25 points. And it's, again, always due a week after. So we're going to finish today. It's going to be due always the night before at midnight. So Monday night at 11:59 p.m. I usually give you some general direction or instructions about it. A lot of the quiz questions I have to manually grade. Some of them will auto grade, but some of them will not. So just at least, try to give me 2 days to get that graded. I try to be very quick, but if I can get it done on Tuesday, I will. But if not, it'll be Wednesday. All right. The other thing is if you want to keep track of dates in the calendar, I'm somebody, I like a calendar and I like mine written down. So I would copy all this into my calendar, but that's up to you. So I've got what chapter we're going to be covering for each of our Zoom sessions and then when those credit quizzes are due. So again, we're doing chapter 1 today. Chapter 1 credit quiz is due Monday at midnight. We're doing chapter 2 on Thursday. So chapter 2 credit quiz is due Wednesday at midnight. All right. So that will be our MO. This will be how it'll work for the whole semester. If you have any questions along the way, please let me know. I'm going to go ahead and get back into my Zoom room. One last thing. This is the periodic table that I really like to use. This is the one you'll be given on each test. And what you'll notice is when we get to chapter 2, we're going to have to start memorizing element names and symbols. Not all of them, but some of them. And when you look at this periodic table, you'll notice some of those element names are there and some of them are not. If the element name is there, that means you do not have to know it. If it's not there, that means you should know it. All right, so this is a good way to kind of quiz yourself, going through it and being like, okay, hydrogen, lithium, sodium, magnesium, potassium, calcium. So that might be helpful, but we'll get to that in chapter 2. All right, I don't see any questions in the chat, so we're going to go get ready with chapter 1 notes. One other thing is my reasoning behind separating the Zoom session into 2 is I just think that 2 hours and 15 minutes of sitting at a desk and listening to a video or to a lecture, it's just a lot. And even for me, I feel like I like the break in the middle to kind of regroup, stay on. It helps me stay on pace a little bit better too, I think. And then also when my computer goes to convert the recording to an MP4, I find that it works much better when I only have an hour versus the 2 hours. And again, also, I think the benefit is that if you want to go back and just look at one part, it's a lot easier to kind of go through an hour video than a 2 hour video. Anyway, that's my logic. If it doesn't work, then we will revisit this. But the only thing that is kind of a pain is that there has to be 2 different links. I literally have to end this meeting so that my computer knows, okay, that's part 1 video. I'll start converting it. And then we'll meet for the part 2 video. So that's why there's 2 links. So at 11:15, you're always going to use this link. And then at 12:30, when we come back, you'll use the second link. All right. So hopefully this works well. But we can adjust as necessary. Okay. So first chapter. Matter, measurement, problem solving. We're going to look at significant figures, prefixes, unit conversions, density, everything that you had in intro chem, just maybe a little new things here and there. So chemistry is the science that seeks to understand the behavior of matter, right? It's the science that studies matter and the changes of matter, which is where it gets interesting. States of matter, for chemistry, solid, liquid, gas are the 3 that we typically stick with. There's others, and I always think that they should include solutions, but solutions aren't pure, so that's the difference. But when we do equation writing, we're familiar with SL, G, or AQ, right, for meaning solution. But anyway, solids are rigid. They have fixed shape, fixed volume. In a liquid form, right, the particles are still pretty tightly packed, but now they have a flexible shape. The volume is still fixed, just meaning that if I take a liter of water from a bottle and I pour it into a bowl, the shape has changed, but it's still a liter, right? Now, if I have a solid ice cube and I take it from a bottle to a bowl, the ice cube doesn't change the shape, right? Unless it melts, that's a different story. But that shape doesn't change, the volume doesn't change. A gas is the most flexible. Gases are mostly empty space. So not only can we have them change their shape, they can change their volume pretty easily as well. If we change the pressure, the temperature, volume is also easily changed. Okay, so those are our 3 states of matter. Then when we look at classifying matter, matter can be classified first into pure substance or a mixture. And the way that you can ask yourself which is which is you can say, okay, are all samples the same? All right, so if the answer is yes, then it's a pure substance. So if I have pure water, just H2O, there's nothing dissolved in it, just pure water. Every sample of water is H2O. It all looks the same. If I have, what's another example? Like a piece of aluminum, right? That the makeup of that aluminum, it always is the same. All right. Now with mixtures, the samples are not the same. Okay. So if I have salt water, for example, okay, salt water from where? From the Gulf, from the Atlantic, or is it a saltwater solution that I made? If I made it, how did I make it? Did I put 10 grams of salt into a liter of water, or did I put 100 grams of salt into a liter of water? Because it's a mix of substances, there's nothing fixed or constant about that composition. It's variable. So that's how you can kind of tell them apart. So pure substance, all samples should be the same. If it's a mixture, the samples, the composition can be variable. All right. Within pure substances, we have elements and compounds. Elements are the simplest unit of matter, simplest form of matter. All right. So that's down here. They are all listed for us on the periodic table. So that makes it easy. And they have symbols like we know, right? Hydrogen, right? H, or sodium from natrium, Na, right? So they are the simplest form of matter. And it's always, I think, interesting to me to think of all matter just being made up of elements in different ratios, combinations, but everything is made up of those building blocks of matter. All right. A compound is when two or more elements are bonded together. So if I have pure water, right, H2O, it's always H2O. There's an oxygen center, two hydrogens attached. If I have something that looks similar, but it's not the same, hydrogen peroxide, H2O2, now I've got two oxygens in the middle, and each oxygen is attached to one hydrogen. So every hydrogen peroxide molecule looks exactly the same, H2O2. Every water molecule looks exactly the same, H2O. Now, if I mix those two together, like when you buy hydrogen peroxide from the store, it is hydrogen peroxide and water. Pure hydrogen peroxide, that's really harsh. It's a strong oxidizer. I worked in the lab as an undergrad. I worked with a 30% hydrogen peroxide solution, and if you got the littlest bit on your finger would turn white, right where it touched. So anyway, what you buy at the store is a mix of hydrogen peroxide and water to dilute it, so it's not quite so strong. And if you can't tell them apart, because you can't, when you look at your hydrogen peroxide solution, it just looks the same throughout. That's going to be homogeneous, right? Homo meaning the same, right? So homogeneous is when it looks the same throughout. You're not going to be able to tell the difference between the hydrogen peroxide molecule and the water molecule, right? They all look the same. It looks uniform. Heterogeneous, though, is when you have things that don't mix very well. So the classic example is when you take oil and water and mix those two together. They don't come together very well at all, right? So heterogeneous, it's still a mixture. We can mix them, but you can tell them apart. All right, so an element is the simplest form of matter. A compound is made up of two or more elements bonded together, all right? And the fixed proportion just means that every water molecule is H2O. Every hydrogen peroxide is H2O2, not H4O4, but H2O2. All right. Now, terminology. We have an atom versus a molecule. So an atom is the term for the simplest unit of an element, whereas a molecule is the term for the simplest unit of a compound. So it's just a language thing. And what I mean by that is you can't have molecules of sodium, just like you can't have atoms of water. Water, two or more elements bonded together, it's a compound, so you have molecules of water, not atoms. Sodium it's an element, it's singular, so you have atoms of sodium, not molecules. So it's just terminology. Atom goes with element, molecule goes with compound. All right. So mixtures, like we talked about, variable composition. Not all samples are going to be the same, right? If we have a homogeneous solution or mixture, that's where it will appear uniform throughout. You won't be able to tell the different substances apart. And heterogeneous is when the composition is it's variable. Like you can see different parts of the mixture. So like imagine going to the beach and taking a sample, a scoop of the beach sand, and you see seashells and other things, right? That's heterogeneous. You can see the different things in that mixture. All right. Chocolate chip cookie, also a good example. All right. So that's first page. Second page, we always get to learn about the scientific method. It's always in there. So scientific method in all science books it has steps to it, right? So step one is you observe something, right? Like Newton and an apple falling out of the tree outside of his window, and he had a hypothesis, an idea. And then you design experiments to test your idea, and you collect your data, and then you think about what the data tells you. And the more and more you do that testing, you can come up with a law or a theory. And what I always love to kind of think about is that everything in your chemistry book is really still just a theory. It's very well tested. It appears to be true, but it's a theory. Like it could be disproven one day. Atomic structure, when we get there, the atomic structure we have now is not the original atomic structure. So at one point, scientists thought that the structure of the atom was very different than what it is now. And with further testing by Rutherford and other scientists, they actually figured out that they had it wrong. And now we have what's called the nuclear model with a nucleus. And that seems to be true, but you never know what might change. Okay. So that's the scientific method. Now, matter, like we said at the beginning, chemistry is the study of matter and the changes of matter. So the first lab that we do is actually looking at properties and changes of matter. You can have physical or chemical changes and properties. So a physical change is when you change the appearance without changing the composition. So that's kind of tricky because a lot of things that change the appearance of the matter are in fact chemical changes. So if you look at a chemical reaction, what you want to focus on is that the reactant, which is the left side of the arrow, looks the same as the product, which is the right side of the arrow, right? That composition of that compound water has not changed. Instead, what you notice is there's a change in the state, right? So liquid to gas, right? Boiling or evaporation, or solid to gas, which is called sublimation. That's dry ice at Halloween time. It's solid carbon dioxide, it sublimates. So a lot of times what I do is I think a physical change is kind of synonymous, although not always, but you think phase change, right? Or a state change where we're changing the solid, liquid, gas, but the composition itself stays constant. So honestly, these are kind of boring, right? We're not really doing anything that exciting here. Another one though, and this is where I always wish that they would use the fourth state of matter, but it's not pure matter, is when we dissolve something. So for example, if I take salt, sodium chloride, all right, and I add water to that, right? So I'm going to just add water to it. Now what's happened is the sodium chloride has dissolved, and now we would mark it as AQ, meaning aqueous or in water. So that is just a phase change. We've changed it from a solid to a solution, but the sodium chloride is still sodium chloride. So dissolving is another physical change. We haven't changed the matter. If we really wanted to, we could evaporate the water and get back the sodium chloride salt crystals, right? The water that we evaporated, if we had a way of collecting that vapor, we could cool it down and turn it back into the liquid phase, right? So physical changes, because we haven't broken any bonds, are typically easy to reverse. All right. A chemical change, on the other hand, very different, right? A chemical change is called a chemical reaction. So in this case, we have broken bonds, we have formed new bonds, and because of that, they are very hard to undo. And what you'll notice is your reactants, everything again on the left of the arrow, are different than what you have on the right, which are your products. In this case, just one, Fe2O3. Now, what you'll notice in this equation, and we'll do equation writing much more in the future, is that we did follow the law of conservation of mass, which means there are 4 iron on both sides, 2 times 4, and there are 6 oxygens on both sides. So we followed the law of conservation of mass, but what happened here is we had iron by itself as an atom, oxygen as a diatomic, meaning 2 molecule, diatomic. What we did is we broke that oxygen-oxygen bond. And then on the product side, we put iron and oxygen and bonded them together. So anytime you change the composition from reactant to product, right, by forming new bonds and new compounds, that is always going to be a chemical change. Now, when you have a chemical change, you typically have things that show you there's new matter formed. So you're going to see a color change, right? And you might think, well, wait, that changes the appearance. So, but that's why it's a little tricky. If you change the appearance as you're going through the reaction, a lot of times that's going to be a chemical change. So a physical change are your state changes. So if I heat something and it boils or it melts, or if I cool something down and it condenses or solidifies, but I'm not adding any other matter to it. It's the composition has stayed the same. And of course, the other one is dissolving, right? Where all we're doing here is changing the state. All right, a physical property is a characteristic. A property is when we describe the matter, and we're describing the matter as it is. We're not doing anything to it. We're not exposing it to anything. We're saying, hey, look at this white solid, right? So you can use color. You can do your state. Is it a solid, liquid, or a gas at room temperature? You can also do density and like melting point or boiling point, because you can use those characteristics to distinguish between matter. Like, for example, if we were going to compare copper and lead, we have color, right? Copper has that beautiful kind of like orangey brownish color to it, whereas lead is like a very dark gray. So that's one characteristic we could use to distinguish the two matters. But density would be another one. Copper, like if we had equal volumes of both, we would definitely feel that lead felt like it weighed more because it has a higher density than the copper. But we're not doing anything to those. We're just looking at these samples and describing the samples. So that's a physical property. A chemical property just describes a chemical change. So basically it's saying what happens to the matter when I do stuff to it. And what that could mean is I try to light it on fire, or I try to react it with a base, or does it corrode over time? Does it oxidize? Does it react with oxygen in the air? But we are adding other matter to it, and that's a chemical property. And again, it's going to change the composition. All right, so it's going to form new matter. So we're going to do a couple of examples here to review what we've talked about so far. All right, so we've got some sentences. We want to figure out if we've got first a pure substance or a mixture, and then we're going to decide if it's a physical change or a chemical change. So in bold, is this a pure substance or a mixture? So evaporation of rubbing alcohol. So this may not be super familiar, but rubbing alcohol is a solution of the alcohol with water. It's called isopropanol. So this, if you're not familiar, when you buy rubbing alcohol at the store, it is isopropanol, and that's not a name that you need to remember, but it's in water. All right. And so because we have two things mixed together, we know that it's a mixture. However, when you use the rubbing alcohol, you can't tell the isopropanol from the water. So that means that this would be a homogeneous or homogeneous mixture. And I've heard both pronunciations. All right, but definitely a mixture because there's two substances in there. Homogeneous though, because it looks the same throughout. All right, so that's the first part. The second part is evaporating. So we know that when we rub the alcohol on our skin, um, it evaporates. And that evaporation process is actually something called an endothermic change. It sucks energy from the surroundings, which is why it feels cold. Because as it's evaporating, it's taking heat with it. And evaporation, because we're just taking it from a liquid and going to the gas phase, that means that that is just a physical change. All right, so that's what we're going to do with each of these examples. We're going to say, okay, whatever's written in bold, is that an element, compound, mixture? And then whatever's happening to that matter, is that a physical or a chemical change? All right, so the second example, we've got propane. And propane, when you get into organic, you get a whole nomenclature system. PROP means 3 carbons. And then ANE means that all of those carbons are saturated with hydrogen, meaning all of the bonding sites have hydrogen on them. So you come up with C3H8. That is a compound of carbon and hydrogen. There's nothing else mixed in there. So this right here is just a compound. All right. And because it is a compound, remember that makes it a pure substance. It's not a mixture. It's just C3H8, C3H8, C3H8 in repetition, right? There's nothing else in there. Not like back up here where you've got the isopropanol in the water. So propane by itself, pure. Now the burning part, the second part, what is this? What type of change is that? Well, it's really hard to undo, right? So burning is always going to be a chemical change. And we may not necessarily know yet what type of change that would create. If you do remember from intro combustion reactions, that's fantastic. If you don't, we're going to revisit this later. But if anybody in here is thinking, wait a minute, C3H8 is a hydrocarbon. Sorry, that 3 came out a little funny. And the fuel for fire is always oxygen from the air. And the carbon turns into CO2 and the hydrogen comes out as water. It's not balanced. We won't worry about that till later. The only reason why I wrote that down is not that you have to know that reaction, just that you can see it's a chemical change, right? New matter is formed. All right. Bonds are broken. New bonds are formed. That's always a chemical change. All right. So next page, page 3, we are going to have the bleaching of hair with a hydrogen peroxide solution. Okay, so solution kind of gives it away. Again, we may not necessarily know. I know I used this in the opening, that pure hydrogen peroxide, you would not want that anywhere near you. But as a solution, remember solution is kind of synonymous with a homogeneous mixture. It means that there's multiple parts. And so in this case, it's hydrogen peroxide and water. And so we can't tell the water from the hydrogen peroxide. So again, that makes it homogeneous or homogeneous. All right. Now, bleaching. One thing is, you may not necessarily know exactly the chemistry behind it, but bleaching, we know we can't undo it, right? Once it's done, it's done. So that means this is going to be a chemical change. We may not know exactly how that happens, like, the chemical reaction, the formula, the breakdown, whatever. But if it's hard to undo, it's more than likely a chemical change. New matter is formed. All right. The other thing is, and this is something we'll talk about in lab, is typically when you have a color change, it signals to you that you have new matter formed. So a color change is typically a chemical change because now there's new matter there, something that wasn't there before. And we see that because we have new physical properties. All right. Then we've got the formation of frost on a cold night. All right. So all that's happening there is we're taking water vapor it's the moisture in the air. And so we're feeling it now, although this morning was quite nice. But normally last few mornings I go out to walk the dog and it's like I'm stepping out into a sauna, so you can feel the stickiness. And when that liquid from the air turns into frost, right, it's just turning into a solid, into little ice frost crystals. So when we see that, we know that that's just a physical change. And the frost itself is just water. So that is just a compound, which would be a pure substance. All right, so that was an example that we've used before. That is a compound. And again, that means that we have a pure substance here. All right. Two more. Okay. Next one is, it says we've got a copper wire that is hammered flat. All right. So copper from cuprum, the original name, symbol is Cu. That we know is singular. So that is an element, which again makes it a pure substance. And if it is hammered, right? And I probably should have highlighted the formation of frost. When it's hammered, right? We're not changing the fact that it's copper. We're just changing the appearance of it. It's still copper, but now we took it from whatever shape it was into a flat shape. So a change in shape, as long as we're not changing the chemical structure, which we're not, it's still copper, then this is just going to be a physical change. So other examples that sometimes books will use for physical change is like folding a sheet of paper, still paper. We've just changed the state, or I'm sorry, the shape. Cutting the piece of paper, carving wood, like mechanically with a hammer and chisel, right? So those would also just be physical changes. All right. And then we've got a match that ignites when struck with a flint. All right. So a couple of things going on here. All right. The ignite, okay, we know that that means burning. So that is going to be a chemical change. Now, I don't really love, this was an example from the book. I don't really love match because what exactly are we talking about? Are we talking about the wood stick with the residue on the top that lights, the phosphorus? Like which part are we trying to get to here? So let's look at match as being a kind of an ambiguous term. I would want to be a little bit more specific, but collectively as a whole, if we think about the match, right, it's got the stick, and my drawing skills are quite poor. And then the top, right? All of that together is a mixture. We can see different substances there. And because we can see the different pieces, the top versus the wooden stick, right, that would make it heterogeneous because we can tell there's different parts to the match. All right. Okay. So that's a look at physical chemical changes, elements, compounds, or mixtures. There's a couple more definitions for us. All right. Energy. We have a whole chapter. I will say Chem 1 is going to feel like we're just reviewing intro for a while, and then we get to the thermochem chapter, which is one of my favorites. It really dives deep into energy changes. But for now, two qualitative terms is if a reaction or process is endothermic or exothermic. And this can apply to both physical and chemical changes. So it's for both. Physical changes can be endothermic or exothermic, just as right along with chemical changes. So it's for both of those. What happens is if it is an endothermic process, the way that I remembered this when I was learning it, endothermic heat flows in to the reaction or to the process, to the change, whatever it is we're doing. If it is exothermic, heat exits the process, whether it's a chemical change or physical change. So that's how I kind of remembered them apart, right? So if it was, let me zoom out just a little bit. If it is exothermic, as that process is occurring, heat or energy exits. Could be energy in the form of light, like think fireworks, the light coming out, that's energy coming out. And as that heat is being released, if we're doing that process in a test tube, your test tube is going to get hot, right? If it's an endothermic process, then energy is sucked into that change, like the evaporation of the alcohol. So the surrounding environment is going to get cold. So, for example, when you step out of the shower and you're all wet, it's going to feel cold, but it's not like someone just turned the thermostat down 10 degrees, right? This temperature hasn't changed. If anything, it might even be warmer in the bathroom because you took a hot shower. But as the water starts to evaporate from your skin, it endothermic, right? It takes energy from your body, that heat from your body, and that's why it feels like it got cold. But it's only because it's an endothermic process. Okay, then energy, there's lots of different terms for energy, work, not too big on these, but I do want you to remember kinetic energy is the energy of motion, movement, right? Potential energy is the energy of position or composition. So if we have a molecule like water, in that water molecule, let me just draw it for you. You've got an oxygen center bonded to two hydrogens. There, in that bond, there is stored energy. So that is potential energy. All right. And if we think back to the propane, right, we know that when we burn propane for our gas grill, it gives off a lot of energy. So there is stored energy in that molecule, right? And if we break those bonds and form new bonds, right, then we'll get more into that when we get into chapter 7, right? And thermal energy, think temperature, right? So thermal energy is associated with the temperature. But temperature is really a measure of molecular movement. So if molecules are moving really fast, temperature is going to be high. And then as they get cold, they move much more slowly, right? So that is in itself, it is a form of kinetic energy, right? Because it's energy of movement. All right. Last thing here is as we go through any kind of chemical change or physical change, energy cannot be created or destroyed. It stays constant. It can transfer from one form to the other. But we'll be looking at that, like I said, chapter 7 with the thermo chapter. Okay. Now, units of measurement. Because we are one of only 3 countries not on the metric system, we have to know unit conversions, right? So we like to use inches, but we should probably be using centimeters, meters, kilometers, right? We like to do miles per hour. We should probably do kilometers per hour. We like to measure gallons. We should probably be in liters, right? There's a lot of units to get us on the metric system. There's conversions that we're going to have to learn for that. So the metric system is really the standard, and I learned it as the MKS system. So M was the standard unit for length rather than inches or feet, right? Or yards, right? A lot of times students think that a meter is 36 inches. It's a yard that's 36 inches, and a meter and a yard are not quite the same. Kilogram is our unit for mass, or gram. Of course, we like to use pounds, so we got to learn that. Kelvin is our gold standard for temperature measurement. We'll be using that when we need to. And seconds is our kind of standard unit of time. All right, so some prefixes. We're going to start there first. All right, with prefixes, I just am fast forwarding here, kind of looking at where my good place to stop will be. Just making sure. Okay. All right. So prefixes. If you had me face to face for intro, I wanted you to remember kilo, centi, and milli. Those were the 3 for intro that I wanted you to remember. There are 3 more now for Chem 1, and that is mega, micro, and nano. And I do need you to memorize these 6. There are others, but I want you to remember these 6. The way they present in Chem 1, which is different than intro, is the book does it where you can swap the prefix with the exponent. So, for example, if I have 1 megaliter, right? Capital M for mega. What that means is I have 1 times 10 to the 6 liters. So you see what it did? It just swapped mega for 10 to the 6. All right. If you have kilo, right? A kilogram or kilogram is 10 to the 3rd grams, right? And 10 to the 3rd is 10 times 10 times 10, right? Which is 1,000. Now here's where it gets different. When the exponent is negative, it's going to look a little bit different than what we had in intro chem. So if I have 1 milliliter, that is equal to 10 to the negative 3 liters, or 1 times 10 to the negative 3 liters. All right, which is the same as 0.001 liters. But back in intro, what we learned was there's 1,000 milliliters in a liter. So what I hope that makes sense is that if I take this conversion that I've underlined in blue and I multiply both sides by 1,000, so 1 times 1,000 becomes 1,000 and 0.001 times 1,000 becomes 1, right? These two statements are the same. 1 milliliter is 0.001 liters, which is the same as 1,000 milliliters is the same as a liter, right? So you can use either one. And a lot of times students don't really want to deal with the exponent. They'll just use what they had back in intro, and that's totally fine. But you'll notice when you're doing the dynamic study guides and other things that if it says, okay, hey, you've got 1 microgram, right? What does that mean? Well, micro is 10 to the negative 6. All right. So mega 10 to the 6, micro 10 to the negative 6. So here's how we're going to practice this. For each of these practice questions that we've got, we're going to replace the exponent that's there with the proper prefix. So 2.05 times 10 to the negative 6 meters, 10 to the negative 6 is micro. So we're going to replace that 10 to the negative 6 with the prefix for micro, which is like a curvy U. That's kind of what I think about it. All right. The next one, it says 4.03 times 10 to the third. 10 to the third is kilo. So this would be the same as writing 4.03 kilograms, right? Because the 10 to the 3 is the same as the kilo prefix. 7.06 times 10 to the negative 9. The 9, it made sense that that was nano. I think because of the double N, it just looked like that made sense to me. So this is 7.06 nanoseconds instead of times 10 to the negative 9, right? All right, and then the last one is 5.15 times 10 to the negative 2. 10 to the negative 2 is centi. All right, so that would be the same as 5.15 centimeters. So again, one thing that may look a little bit different, if we think about the intro chem way, we learned that there's 100 centimeters in a meter, right? Now, what this book is asking you to do is say, okay, well, just replace the prefix. So now the 1 goes with wherever the prefix is. Replace the prefix with the correct exponent. So 1 centimeter is 10 to the negative 2 meters, which is the same as 0.01 meters, right? So that's why it may look a little bit different initially. All right, next problem we're going to do is we're going to work on getting everything into what's called proper scientific notation, and then we will replace it with the exponent, or sorry, the prefix. So when I have 6,217 grams, proper scientific notation says that I'm going to move the decimal to follow the first non-zero digit. That's the key. You got to move it to where there's only one number in front of the decimal. So we're going to move our decimal 1, 2, 3 spots to the left. So we move the decimal 3 spots to the left. So the exponent is a positive 3. All right, so that's what we have here. So 6.217 times 10 to the third, and then there's our unit of grams. Now that we know that the exponent is times 10 to the third, we can replace that with kilo. All right, so on the next one, we're going to go 0.0016 seconds, but we're going to move that decimal 1, 2, 3 spots now to the right. So we move decimal 3 to the right. So when you move it to the right, it's negative on the power. So it's going to be times 10 to the negative 3. So this is going to be the same as 1.6 times 10 to the negative 3 seconds. And then we go up to our prefix chart if we need to. and 10 to the negative 3 is the same as milli. So I'm going to replace that times 10 to the 3 with milli. So this is 1.6 milliseconds, ms. All right. 2 more to go. We have 0.0717. So here I'm going to move the decimal 2 to the right. So we move decimal 2 to the right. So that means the power is going to be a negative 2. So anytime you move it to the right, you're going to put negative on the exponent. So this is going to be 7.17 times 10 to the negative 2 grams. And then I'm going to go up to my little prefix part and figure out what do I replace 10 to the negative 2 with. So 10 to the negative 2 is centi. So I'm going to write this as 7.17 centigrams. All right. And then one more to go. And on this one, we have to, oh yeah, thank you. So there's in the chat, fun way to remember, Lars. If you're moving to the left, right? So if you're moving your decimal to the left, you're going to add. So if you're going to go to the left, you add. And then if you're moving the decimal to the right, like we did for B and C, then you're going to subtract or take the negative on the exponent. So thank you, Avery. So Lars, moving the decimal to the left, you add, so positive. If you're moving the decimal to the right, you subtract, so negative. Okay, that's a good one. I didn't know that one. Okay, last one here. And for this one, we have to talk about significant figures a little bit. Now, that's going to come in our second session, so we're not going to harp on it too much just yet. But in this 3,870, the 0 here, because it's not marked with a decimal, we think it's just a placeholder, meaning it's there for magnitude only, that it's not actually a measured digit. And we'll talk about that more when we get to part 2. So if you're like, I don't remember that, then don't worry, it'll come in the next video. If you're like, oh yeah, I remember that, what you're going to see is when I move my decimal 1, 2, 3 to the left, right? So again, we're moving the decimal 3 to the left. So it's going to be adding. So adding positive 3 to the exponent. When I write this in scientific notation, that 0 is going to go away. So it's going to be 3.87 because the 0 is not a sig fig. And it would be times 10 to the third meters. And 10 to the third, like we saw earlier, is kilo. All right, so we're going to swap that 10 to the positive 3 to kilo. And I forgot to highlight these parts too. Okay. All right, 4 more examples, and then we're going to take a break because I know we're getting close to the end of the first hour. Now what we're doing here is we're going to replace the prefix with the correct exponent and then put it into scientific notation, proper scientific notation using Lars. All right. So when I had 355 microseconds, what I first did here was replace the micro with times 10 to the negative 6. All right, that's the first thing I did. Then the second thing I did was put it into proper scientific notation. And what I needed to do here was move the decimal 1, 2, right? We moved it 2 to the left, and left means add. So it went from negative 6 added 2. That means it becomes a negative 4. So we added 2 plus negative 6 plus 2 gets me to a negative 4. For the next one, first thing I need to look at is kilo. So 1885 kilo would be times 10 to the third meters. So that's the first part. It's replacing the kilo with 10 to the third. All right, and then to move it into scientific notation, proper, we're going to move the decimal 1, 2, 3 to the left. All right, so move 3 spaces to the left. So we're going to be adding 3. So when I put this into scientific notation, proper, 1.885, should have left more space. And then instead of times 10 to the third, we're going to do 3 plus 3. So it's going to become 10 to the 6, right? And then the unit there would be meters. Sorry, I didn't leave enough space for that. Okay, 2 more. 1,350 centimeters. Okay, so if I go back up to the top, centi means 10 to the negative 2. All right, and then on this one, we are again moving 1, 2, 3 spots to the left. So let me put that way out here. So again, moving 3 to the left, we're going to add 3 to the exponent. So this is going to become 1.35. 10 to the negative 2 plus 3 becomes 10 to the 1. And you can just put times 10 or 10 to the 1 meter. Either way, 10 to the 1 is still just 10. All right, last one. 425 nanometers. Okay, so nano is 10 to the negative 9. So we have 425 times 10 to the negative 9, meters. All right, and then proper scientific notation, we're moving it 1, 2 spots to the left, or yep, move 2 to the left. So we're adding 2 to the exponent. So this would be 4.25. Negative 9 plus 2 is negative 7 meters. All right. Okay, so this is my plan each week. We're going to talk for about an hour and 15, an hour or so. Then we're going to take a nice little break. Okay, so I'm going to make a little note on my notes. This is where the part 2 video is going to pick up. And so what I'm going to ask is at 12:30, if you would use that second link to come back into my lecture. Sorry, I know this may seem a little cumbersome to have to like exit and come back. But again, I think this is going to make it better when I post the videos. So we're going to cut here for this first part. I'll meet you back for the second part in that second posted link on the course homepage. So I'll see you back here at 12:30.